Hello and hi all. Let us talk about Oppenauer oxidation. As the name suggests, it is an oxidation reaction in which an alcohol gets converted into an aldehyde or a ketone, depending upon the alcohol. If alcohol is primary alcohol, then it will be aldehyde, and if it is a secondary alcohol, this will be converted into a ketone. So Oppenauer oxidation converts alcohol into its corresponding carbonyl species. The reagent used is usually an aluminum alkoxide, like aluminum isopropoxide or aluminum isopropoxide, and also a ketone. So ketone should be there to accept this hydride from this alcohol so that this alcohol can be converted into a ketone or aldehyde in this case. So if it is a primary alcohol, this will be converted into an aldehyde, and if it is a secondary alcohol, this will be converted into a ketone. So there should be a hydride transfer. So tertiary alcohol does not give this reaction. Now let us explore the mechanism. So in this reaction, you can see this ketone is also being used. This here we show it as an acetone, which is cheap ketone. To avoid certain side reactions, you can use ketones without any alpha hydrogen atoms. So in general, in this reaction, a ketone reacts with an alcohol in presence of aluminum isopropoxide. This alcohol will get oxidized into corresponding ketone or aldehyde depending on the alcohol, and the ketone will get reduced into corresponding alcohol. So this ketone, this acetone will get converted into isopropanol. So our desired product is a ketone, then it is an oxidation reaction. If our desired product is an alcohol, then this is a reduction reaction. When it is an alcohol, when our desired product is a ketone or aldehyde, this oxidation reaction we call it as Oppenauer oxidation, and we choose reagents accordingly. And if alcohol is our desired product, this ketone is getting reduced and our reaction is MPV reduction. Okay, so that's an interesting factor here. So let us explore that mechanism. Now, alcohol will react with aluminum isopropoxide or any aluminum alkoxide or any aluminum, diethyl aluminum alkoxide or something like that. Then, so there is going to be a new bond between oxygen and aluminum. Then oxygen will have a positive charge, as the 2 electrons in oxygen is going to make the bond, and oxygen will lose 1 electron. As in this bond, this is the new bond. In this bond, only 1 electron belongs to oxygen and 1 electron belongs to aluminum now. Now both electrons were on oxygen, and now oxygen lost one of its electron, so oxygen will have a positive charge. So this H plus can be picked up, and we can show the resonance arrow, like curved arrow like that. And now this negative charge species, that is this, as a result of this bond breaking, you will have this alkoxide, isopropoxide, and this will pick up this proton from here. And you will have this species in our starting material. This alcohol is completely coordinated with or bonded to aluminum with the elimination of an isopropanol group from aluminum. We could write this one as minus isopropanol. We don't need to write this here. And this aluminum is still Lewis acid. It is still electron deficient, and this can accept electrons from the ketone. So that's how the reaction goes. So there is lone pair on oxygen that can attack aluminum or coordinate with aluminum. So this means there's going to be a new bond between this oxygen and aluminum at the expense of this lone pair, like this. This aluminum will have a negative charge as aluminum gained 1 electron, while this oxygen will have a positive charge as oxygen lost one of its electrons. So let's put charge on oxygen too. Now the hydride shift happens. Remember, there is a hydrogen here. As this is a secondary alcohol, obviously there is a hydrogen. We should show it now, as we are showing the hydride shift here. Hydride shift can be shown as something like this curved arrow. This means this hydride, this hydrogen with its electrons. So these 2 electrons will no longer be in between this hydrogen and this carbon. they will be in between this hydrogen and this carbon. I mean, this carbonyl carbon. That's what is meant by this curved arrow. As a new bond is forming to this carbon, an old bond will break. So let us show it like this. As there is a new bond here, an old bond will break. So that's, you can show it like that. So this curved arrow means this pi bond is going to break and both electrons are going to stay on this oxygen. This happens through a 6-membered transition state. Let us show it like that. So while this oxygen aluminum sigma bond is breaking, this oxygen carbon pi bond is forming, this carbon hydrogen sigma bond is breaking and getting weaker, and this hydrogen carbon sigma bond is forming or getting stronger, and this oxygen carbon pi bond is breaking or getting weaker. Now that's the transition state. Altogether the charge is neutral. This aluminum oxygen bond is breaking while this oxygen carbon bond is forming. Let us show that this oxygen carbon bond is forming and this bond is breaking. Now this bond is breaking. I'll show that. So now we have this ketone left. So I mean this oxidation of this species is complete. So let's do the, now this hydrogen carbon bond is forming and this fully formed now. This carbon oxygen bond is breaking, and let's show it like that. So now we have a structure like this. So this is the ketone. So oxidation is complete. Our alcohol got converted into a ketone. Hydrate transfer is complete. Now this aluminum species is still aluminum isopropoxide, and this can do the reaction again. So this will act as the catalyst, and this alcohol will continuously get converted into ketone, corresponding ketone. So let us go over this reaction once again. This is Oppenauer oxidation. Primary alcohol get converted into aldehyde, while secondary alcohol get converted into ketone. We need aluminum isopropoxide or a similar reagent of aluminum. So this alcohol oxygen will get coordinated to aluminum or aluminium species, and you will have a structure like this, and this proton will be picked up by this isopropoxide group. After removal of isopropanol, we will have a species like this, and the ketone will coordinate with this aluminum species. So we will have a structure like this. So in that structure, hydride transfer can happen. That is facilitated by this bond breaking and bond forming. All this happens through a 6-membered transition state like this. Obviously, this is a chair-like transition state or pseudo-chair transition state. This will get converted into corresponding ketone, and this aluminum isopropoxide group or aluminum isopropoxide got regenerated here. This aluminum can get coordinated with the alcohol and again can oxidize that into a ketone like this. The same mechanism goes on. One more interesting thing about this reaction, here in this reaction, a ketone is getting converted into its corresponding alcohol, while the alcohol is getting converted into corresponding aldehyde or ketone. So if our desired product is ketone or aldehyde, we will use a cheap ketone as the reagent, and you will have this aldehyde or ketone as the product, and it's basically oxidation, and we will call it as Oppenauer oxidation. And if we want the alcohol, we will use alcohol like a cheaper alcohol here, that is like an isopropanol. Our ketone, our starting material which is needed to be reduced, will be here, and that will get converted into our desired product alcohol. So then we call it as MPV reduction, Mervin-Pontroff-Verley reduction. Oppenauer oxidation and MPV reduction both are same reaction. If our desired product is ketone or aldehyde, we call it as Oppenauer oxidation. If our desired product is alcohol, then we call it as MPV reduction. Hope you understood what I'm trying to say here, and I hope you understood the mechanism of Oppenauer oxidation and MPV reduction, so to say. Thank you.